Okay, so today I thought we would look at two problems that both involve particles moving through magnetic fields as projectiles. So the first one we're looking at here is we have some particle, it has a mass m, it has a charge plus q. So we're imagining it's a little point particle that's positively charged. We're launching it with some speed, we'll call it v naught, at a 45-degree angle. We'll just kind of keep this simple and launch it at 45 degrees. And what happens is this particle moves under the influence of gravity, the usual way. But then right at its apex, it enters a region of a uniform magnetic field that's directed into the board. That's all these little X's here. And the B field is shown in blue. It persists in that region for some time, moving horizontally, and then eventually it exits that region and continues the back half of its projectile motion, landing some distance away. And the question here is, what must the magnetic field strength be, the uniform magnetic field strength, to affect this kind of motion? So what we're going to do here is we're going to look at Newton's laws, well, really the net force, on this projectile as it's moving horizontally through this region. Now, this is kind of a contrived example because, well, we know it's being launched at 45, so I'm not leaving theta as a variable, although we easily could. And we're assuming that it enters this magnetic field right at the moment that it's reaching its apex, just to keep the maths kind of simple for this first example. So let's go ahead. We'll write down Newton's second law. So first off, we're going to write down the net force on this object as it's moving through this magnetic field. Now, there are two forces acting on it. One is the gravitational field, and I'll go ahead and write that in the j hat direction. So we have a mass m moving in a field g. Of course, that g is pointing downwards, so there's a gravitational force. And then we're going to add on to this the magnetic force, the Lorentz force. Now, we're assuming this is not moving relativistically or anything, so we're just going to be using our standard q v cross b term for the magnetic force on this particle that's moving in this magnetic field. Luckily for us, b happens to be uniform, and v is in a very particular direction while it's moving through horizontally. So this will be kind of straightforward. Now notice that because it's moving directly horizontally, it is not falling or rising. It's not changing its direction of its velocity. And because there are no horizontal forces, we'll see kind of why that is in a sec, but these magnetic fields cannot change the speed of the particle. Not only is the direction constant, but its magnitude is also. So that means that the acceleration of this object in the magnetic field, at least for this very particularly chosen path, is zero. The net force has to equal zero. I'll write that as the zero vector. So now what we want to do is go solve for B, find out what this magnetic field is. We'll also have to do a little kinematics to know what is the speed of this particle as it's moving through. We know its launch speed is v naught, but we kind of want to know what its speed through here is, and we know it's going to be a little slower because gravity's done some work on it. Okay, so let's combine a couple facts. From either kinematics or just energy conservation, and maybe I'll appeal to energy conservation, we can quickly find out what this velocity is here in terms of v naught. And since this is a 45-degree angle, we kind of know that, well, since the gravitational force does not exert any influence in the horizontal direction, once it's reached the apex, this v is simply the x velocity of the initial particle. Again, gravity is doing work in this vertical direction, and we know that the gravitational force is going to cause the y component to drop until it's zero at this point. So all that will be left over is the horizontal component. And that's pretty clearly just v naught cosine of that initial launch angle, and in this particular case, we know what that angle is. So I'll get a v naught over root 2 for the cosine of 45. Now, figuring out this direction, this cross product involves the velocity vector going to the right and this magnetic field vector going into the page. Now, we all remember our right-hand rules, right, for calculating these cross products. So I'm going to take the thumb of my right hand and stick it in the direction of the first vector, that's to the right. Take the finger of my right hand and stick it in the direction of the second vector, that's into the board. And then my third finger, which is my middle finger, will point in the direction of the cross product, which sure enough is up. That's a good thing because we are expecting two things to add to zero. The first one's negative. This one better be positive since we were told that Q is positive. This is also just sort of a sanity check to make sure that the direction that was shown in the problem is correct. Into the board is required if I want this thing to move horizontally. So in other words, I can just write this whole thing as negative mg, and I'm going to look at just the y component because we know that's all that's going to be involved. And then I'll have a plus qvb. You might say, well, what about the magnitude? If you want to find the magnitude of a cross product, you can remember that you just multiply the magnitudes of the two vectors that make it up, that's v and b, times the sine, S-I-N-E, of the angle between those two vectors. But look, v is that way, b is that way. That's a 90-degree angle between those, so the sine is 1. And we already decided it was positive, so this has to equal 0. And now a very simple little final calculation will let me calculate b. Moving things around, I'll have mg over qv, and then I'll go ahead and also replace my v with v naught over root 2. Okay, pretty easy. We found our magnetic field strength. If you want to be completely finished here, we should probably write this as a vector by affixing a unit vector. Now, pretty clearly, we already know it's going to be pointing into the board, and if we're using our standard right-handed coordinate system, which we have to be because we're using the right-hand rule, x cross y is out of the board, so I need to put a minus, and maybe I'll put a k hat on here so we know it's into the negative z direction. And there it is. This is our uniform magnetic field that causes this type of motion. Okay, now let's look at our second problem. Okay, here's the second problem. So here we have, again, a projectile is emerging this time from a uniform magnetic field. It is emerging, moving directly in the right-hand direction. So we know that, again, the gravitational and magnetic forces are balanced initially. Then it exits the region that has this magnetic field at some height h above the ground. The charge is still plus q, the mass is still m, and then it will fall, and I want to know how far away does it land, this L. Now notice here I did not give you v. We don't know what this initial velocity is, but of course, the equilibrium condition on forces is going to give us that for free. So it's very similar to the previous problem. Let's just work it out. I'm going to start by looking at the net force, again, in this region where it's moving at constant velocity to the right. And just like before, we'll have a gravitational force downwards, and we'll have a Lorentz magnetic force upwards, and it's not accelerating because it is moving to the right at constant speed. The exact same argument from before follows through. You can do your right-hand rule. Remember, v is this way, b is into the board, so my magnetic force is up. And then the magnitude of v cross b will just be vb times the sine of 90 degrees. So from all of that, I can go immediately solve for what v is. I'm just going to have mg divided by qb. Okay, so that is the velocity that it emerges from this magnetic field with. And now it is a very simple, straightforward kinematics problem to figure out how far away this lands. As a reminder, I can write down my two kinematics equations. Since it's been a while, maybe we'll just practice that real quick. Of course, we're assuming that there is a constant gravitational acceleration. The final position I want it to land is this thing x. I want to find out what that is, and I've chosen coordinates that are kind of shown here. So we're going to start at x not equals 0. This v is this v. That is the initial x velocity as it emerges here. I don't know what time it takes. We're going to eliminate that, but I do know that it's not accelerating in the x direction. The final position in the y direction is, well, the ground. So it hits the ground at 0, and it starts at some height we'll call h. It does not have any initial vertical velocity component, so that's 0, but it does accelerate downwards at minus g. So now I want to combine these two equations by eliminating t and solving for L. So putting it all together, we're going to have L is v, that's this value we have right here, times t. A very quick little bit of algebra shows you that t is going to be the square root of 2h over g. And honestly, that's probably fine. You could, if you want, bring this g inside. I don't know that it's really that useful, but why not practice our algebra a little bit? And there we have it. Here is the distance at which this particle lands in terms of the given parameters of the problem. And there's our second problem. QED.